Hello and welcome to Facebook Live from downtown Mountain View at the SETI Institute. My name's Simon Steele. I'm the Senior Director of Education here at the Institute, and I'm speaking to Pablo Sobron about a new mission called InVADER. And we're going to talk about the mission, what it's doing, and its potential reach in terms of moon exploration in the solar system. And all of this stuff you'll see today will be posting online, so you'll have all the resources. And if you have any questions as we go on today, please do send us a message on Facebook, and we'll try and answer as many questions as we can. So first of all, Pablo, like any good NASA mission, InVADER is an acronym. So what does it stand for?
Yeah, so what we're trying to convey in the title, which is a mouthful, as you will say, is a little bit what we're doing. And so specifically the instrument or the mission stands for In Situ Vent Analysis Dive Bot for Exobiology Research. So very complicated way to explain that we're just basically sending a robot down into the bottom of the ocean.
Okay,
Yeah.
So this is not a space invader, this is an ocean invader.
It is an ocean invader.
Yes.
Of sorts.
Of sorts. And so there's a couple of cool words in there. There's divebot, which we're going to learn about, and there's also vent, and we're talking here about something venting under the ocean. And so maybe we'll take a look and see where InVADER's going, and then we can see what it's going to explore.
Yeah, great. Yeah, let me show you where we're going. So turns out that in places on Earth where the tectonic plates collide with each other, there is cracks, and there is spaces through which fluid coming from deep into the Earth, which is hot and rich in elements and chemistry, it can just come out as a vent. Think about it as a volcano, if you want, where you have water coming from the ocean, seeps into the rock, gets close to the core, heats up, boils, and comes out as a vent in the seafloor. And specifically the seafloor area, or the vents where we're going, as you can see in the map here, are located a couple of 100 miles off the coast of Oregon. And this is a very special place called Juan de Fuca, and there is a lot of activity. There's a lot of these mini or chimneys or volcanoes, vents, if you want. And what we're trying to do is to bring our mission all the way down there. And there's been people who've brought samples back. There is instruments going on there, and as a matter of fact, the NSF, the National Science Foundation, runs a program there. It's called the Ocean Observatory Initiative, which aims to understand that area much better. So they have laid out a series of stations with cables, with power stations, so scientists like us can bring in a mission down there and can explore, analyze, and learn things about the bottom of the ocean.
Okay. Now you say bottom of the ocean. We're off the coast now of North America. We're sitting on the edge of one of these tectonic plates, where we've got stuff coming up because there's a crack in the surface of the Earth. How far down is this stuff? How far down in the ocean do you have to go?
So we're going to go 1.5 kilometers, so almost a mile down, which doesn't seem like a lot. But if you've done ocean sciences or you know something about the ocean, divers usually don't go, scuba divers don't go usually below 100 meters because the pressure is so high that it's difficult to do anything down there, including breathing, especially breathing. So we're dealing with, at 1 kilometer, 1.5 kilometers in this case, we're dealing with very high pressure. So the challenge is to build structures that can survive that pressure. And so we call it deep ocean, and although we know that the deepest point of the ocean is about 11 kilometers, but this is already pretty extreme environment.
Okay, and that deep, is it dark? You'll need floodlights on InVADER. Is there much sunlight that gets down that deep?
So there's no sunlight. There's there's so much water in between the surface and where we are that all the photons get scattered and get lost. So it's pitch black. It's totally dark, and there are some organisms, some bacteria, some shrimp maybe, that actually use light. They think about like small flashlights, and they use that to communicate with each other. But that's pretty much the only light that we have there. So in order to do our science there, we need to bring lights to do videos and images, and we also need to bring lasers to actually do the science that we want to do.
Okay. So shrimps with flashing lights, I mean, that's about as alien as you can get, isn't it? So
yeah. Especially down there when most of the organisms are adapted to not need vision. The shrimps use the vision or these lights to actually communicate and to alert each other about threats or about other phenomena happening there.
Okay, so we'll have a look at what InVADER looks like in a second, but just a little bit more about these vents. You say they're like sort of ocean volcanoes. They got stuff coming up from the Earth's mantle, which is spewing into the ocean. What sort of scale have we got to sort of give us an idea of how big one of these would be, or one of the ones that you're exploring?
So the range of vent volume or size or height, if you want, things can go from 1 meter or 3 feet all the way up to 100 meters in elevation or in height, right, which is like 300 feet. So the one where we're going to is located in a place called Axial Seamount, and we're looking at the Inferno chimney in particular. That's our target landing site. And this one is about 4 to 5 meters tall. Okay. And one of the interesting things about these systems is that they're alive. So you see venting almost 24/7. And
so you haven't got to wait for it to go off like a volcano. Yes.
It eventually can go off, and that's one of the reasons why NSF is looking into this place, and they're actually liking our mission, is because we're going to be able to determine the chemistry, and chemistry is a good predictor for potential seismic activity. So in order to predict earthquakes or tsunamis that come after the earthquakes and will hit the coast eventually, these systems like ours and like NSF's are being able to monitor this activity. And so, but because the chimneys or the vents are alive, they're continuously changing, the shape changes all the time. And they grow, eventually currents come in, knock them over, or somebody comes in with a robot and knocks them over. And so they're constantly changing. So that's why we're about a year away from deployment, from launch, and we still don't quite know where we're going to land because, again, the environment is very, very much dynamic, which makes it very interesting.
Okay, let's have a look at what InVADER looks like.
Yeah.
That might be interesting.
So what you can see in the screen now is just the design, or is this our aspirational instrument or mission. And what we have here on the top, on the tower on the left, you see a little tube cylinder, a little bottle, as we call it. And this is what contains all our scientific instrumentation. And what we have there is a green laser, and you can see a picture of a green laser shooting into a rock in the middle of the screen. And that will be able to shoot anywhere from 1 meter to 5 meters away from the vent, and we'll be able to move it up and down, left and right. So this tower is static. You see 3 feet there in the bottom with a power supply. There's another cylinder down below. And we want to land it, want to park it down in the seafloor, and by using mechanical actuators, we'll be able to move our laser up, down, left, right, and do that over the course of a year. So the idea is to monitor the growth and the changes in chemistry, and minerals, and life, organic matter, there over the course of a year at high frequency, every day, more or less. And not only that, but we have a secondary payload, which is a sampling instrument. It's a drill that is going to be able to touch the chimney, the black smoker, and drill a core into the chimney and bring the core back to Earth. So in a sense, we're doing a sample return mission in which we're going down there, we're going to explore the vent, find what's interesting about it, and determine what places are the most interesting to sample, then deploy our drill, get up to 12 samples at a given time, and bring them up to the lab here, where our scientists can use the state-of-the-art equipment in the lab to determine what the chimney is really made of.
Okay. So like any good InVADER, it's equipped with lasers, which is good because you have to defend yourself. But what else are lasers? You know, you're shooting lasers at this chimney, and that's telling you something about what the chimney is made of, about the chemistry. Can you put it in very simple terms how you, by shooting a laser at something, you can tell what something's made of?
Yeah, I can show you exactly how we're gonna do this, and the way we envision our mission, the way we're testing it and building it, and it works for now, is that with a laser we can do at least 3 different things. First of all, we take a picture, high resolution picture. That will be the first row of 5 images you see there on the screen, and that's a very high resolution image at about less than 1 millimeter per pixel. So we have a very, very good way to assess whether we're going to hit something of a given color, We can see the texture. We can see how big the grains are in minerals, and perhaps if there is any organic mat, any moss or any algae, or perhaps crabs, which have been seen there. And so that will be our first survey, our first impression of the vent. And then when we assess the places we like most, then when we fire the laser, and you can see a picture or a video, hopefully it's working or not in the screen, but you can see the green beam on the left picture that is shooting. That is, I think now you can see it.
Good.
So this is a since we're not ready to dive deep yet. We're bringing a sample to the lab, and we're testing everything in the lab first before. Like good scientists, we don't want to try to make sure we don't break it.
You don't want to get down there and press the on switch and nothing happens.
Exactly, because you cannot send a mechanic down there to fix it, unfortunately. So what we're doing is we shoot the laser. And the laser gives us a lot of information. One of the most important outputs of this laser is we can see all the minerals that you have there, and that will be the second row of pictures you have there, which are called spectra. It's Raman spectra in this case, and what you see is plots, is lines with different sharp peaks, and each of these peaks tells you what the vent is made of in terms of minerals. And things that we can see here in the vents that we're going to analyze, we expect to see a lot of sulfides, especially like pyrite, something that looks like gold. So this yellow picture you see here is called fool's gold, because it looks like gold, but it's not. It's just iron sulfide, so sulfur and iron. So we can see the distribution of different minerals on these chimneys, and more things that we can learn from the laser is in the third line here. This is the Lipse intensity plots, and these are lines where you see very sharp peaks, and in this case the peaks tell you what elements do you have there. So combining the minerals and the molecules with the elements, we can really constrain what the geochemical composition of our sample is. And third, or last but not least, some things that you can see in both of these spectra and the lines here, you can see that they're not flat. They don't show like a flat line and then a sharp peak. They show a little bit of a background, like a big, I don't know how to call it, like a line, baseline we call it, or a line where that's fluorescence. And that's the reason why you see the green beam into the fish tank there on the left. That's because the matter, or usually organic matter that is present in the water, it likes to absorb this laser and then fluoresce and give you this green glow. So that we can analyze as well. And this is very indicative of what kind of organic compounds, and some of them that are attached or are associated with life, we can actually determine this as well. So just to summarize, we'll see in the image that tells you everything about what it looks like. We have the chemistry, elements, we have the minerals or molecules, and we also have the organic content. So it's a combined payload to analyze all of this in a contextual way.
Okay, so you know the elements there, organics, minerals, and everything. Does that, and the next step up is, are there things swimming around in these vents, at various sizes? Obviously, we said there were shrimps with lights on their heads, but is there anything sort of more fundamental happening in these vents? Because I've heard that these vents are, there's a possibility that this is where life on Earth started. So is your experiment heading that way to answer some questions? Yeah.
So one of the angles that we're trying to attack here, as you mentioned, is the origin of life. It's what happens down there at the fundamental level, at the chemical level, is that you have ocean water, which is very cold, 2 degrees centigrade, 34 Fahrenheit. And it's basically just salt and water. There's not much going on there. It's a very, very boring system, arguably. And then what happens is when you see these vents coming up, and you've seen this in the pictures, they're black or white. They're just very, very strange, very different than the ocean. So the reason why they're different is because it's full of chemicals, right? And it's high temperature fluids. In this case, it's acidic, so it's low pH, and it's full of elements, full of iron, full of sulfur, gold, silver, phosphorus. It's a rich soup of elements that is coming with water at a high temperature. So what happens is that when this vent encounters the cold water, there is a shock, if you want, like we call it a gradient in chemical composition, and it turns out that life is. If you think about life as an engine, as a machine, life is fantastically efficient at harnessing these disequilibria, these gradients in chemistry. High chemistry, low chemistry, life loves those situations where it can take the extremes, use it to their advantage, and generate metabolism. So that's one of the reasons why the vents have been proposed as one of the most plausible places where life started on Earth. And by association, since we know that there are oceans of liquid water in certain moons of our solar system, so you have in Jupiter, you have Europa, and other icy moons that we do know for real now, after modeling and a lot of efforts for missions, that there is a crust of ice that seals global oceans underneath, oceans that are made of salty water, very much like our ocean. Same happens in Enceladus, a moon of Saturn, which not only we know it has water, liquid water, but it has the jets, the plumes that are seen on space. And we've all seen these pictures of Cassini flying through one of these plumes and getting a little bit of the chemistry. And Cassini was able to determine that these plumes contained silica and certain alcohols that are only found in vents, like the ones we're going to analyze here on Earth. So now using kind of the progression of, not only we're trying to answer the question of, well, did life indeed started on these vents on Earth, but since we have these vents in space, did life ever emerge in these vents in space? So that's a whole different NASA program, and not only NASA, but internationally supported program that is trying to look at these moons as potential analog or potential other origins of life on our own solar system. So hence our project is trying to bridge both fields, the exploring new vents in other planets or moons, and learning more about our own planet.
Okay, cool. I'm just going to take a break before we dive into the moons of Jupiter. I've got people all over the world listening. Welcome from Germany, Louisiana, Oklahoma, some people from Scotland, New Zealand, Mexico City, and Australia. So that's pretty much all of this planet covered.
That's excellent.
Which is wonderful. So this, can you see this as a prototype for these landers on Europa one day? Are you seeing that this is your ultimate goal? I presume, to actually get one of these, stick it on a lander, and get through the ice.
Yeah, that would be a very long-term vision of what we want to do. But yeah, definitely. So part of the reason why NASA supports this project and likes it is that it's a precursor of a potential future mission to one of these moons. Now there are a lot of problems with going to Europa, a lot of problems to going to Enceladus that we have to solve before we ever think about bringing a submarine or a submersible to these systems. But you gotta start somewhere. And in this case, we're one of the very first teams that is creating an integrated payload, very much like a mission. They're gonna be able to test it and advance. More importantly, we're gonna learn what kind of technologies and techniques we need to develop further to eventually go to other planets or other moons and make them useful to answer the scientific questions when we're there.
Yeah, okay. Okay, I got a question from Ron here. Did he say shrimps with flashlights? Okay, so of all of this, all the technology that we're talking about in Jupiter, yes, the shrimps with flashlights, I think, is going to be the take-home message, isn't it?
Yeah,
so
well, I think more than a shrimp with a flashlight, think about a shrimp as a flashlight. So we're talking about shrimps that at the chemical level internally, they're able to generate light. Some animals generate sound, like we are when we speak. Some other animals, like this shrimp, are able to communicate through light. Think about in the summer you have fireflies, right? So it's the same system. Chemically, they're able to generate light.
Okay, I'm going to come back to that question.
Apparently, we have a very interesting question.
Oh, no, I am told by the controller here. Tell people to share this video, this Facebook video. Please do share this with friends and everyone to learn more about this exciting mission, which is still sitting in the lab in where? Where is
So this is a very, and I'm going to show you one more slide that contains not only it's a summary of what we're trying to do, but it also shows all the institutions that are part of this project. And you can, if you look at the website, which I believe there is a link in the page, and you can dig into who's who and who's doing what. But basically, it's an enormous team. It's a team made of 10, 15 different institutions around the world, mostly US, but there's international collaborators. And right now we have a team in the University of Hawaii who are building the laser system. We have a team in Honeybee Robotics who are building the drills and the sampling system. We have a whole science team at JPL that is building a computer model and the deep learning that is going to require to, or machine learning, AI even, to control and to analyze all the data that we're going to generate. There's teams at different universities that are doing science support with experts in ocean geochemistry. And very importantly, we have the builders and the architects of the whole tower that you saw earlier at the University of Washington in Seattle, the Applied Physics Laboratory there. They're the ones who are, once we finish the design and the build of the prototype, they're going to take over and they're going to make sure it's watertight. And they're going to make sure that we're able to bring it down there with another robot. And they're going to plug us into the cable, and we're going to run all the operations, and we're going to run all the mission control down in Seattle. So for us, will be not Houston, we have a problem. It will be Seattle, we have a problem. If anything happens, which we don't expect so, but it's a very, very big team that includes, and I leave it for the end, but our team, we have Citrus College down in Los Angeles area, who is doing a fantastic job at bringing STEM students from minorities in the area. And we've been able to have kids from different backgrounds who are eager to learn about science, technology. They're super excited about this, and they're coming around different teams, talking to the scientists, engineers, learning a lot about this project, and hopefully we're training the next generation of ocean experts and space experts at the same time out of Citrus College.
And they will follow the program, I imagine, as it continues and as it operates. They can see the results coming in.
We have a multi-year project, so hopefully we'll be able to extend this for many more years to come. But these are the kids that eventually will be able to learn way more.
To take your job,
and perhaps they'll be the ones who will discover life on Europa. So we're very happy to be able to work very, very close together with young scientists. And if there is any young scientist in the audience, or a young high school student who wants to be a scientist, please contact us. We always have opportunities to engage with young people eager to learn.
Yeah, that sounds good. Yes, please do. Write in if you have any questions about that. If you're interested in this sort of thing when you grow up, then please do get in touch with us. So this is basically a space mission, except it's down instead of up, and you can plug this one in. You say so, which you can't do with the Europa lander, unfortunately.
And there's one thing that a lot of people don't realize is that it is. I'm going to say this knowingly. So it is often more difficult to design, deploy, and operate a mission in the deep ocean than it is to do it on the moon or on space in general. And the reason is that we're very good at making things that can withstand the vacuum. So satellites, moon, Mars, easy. Well, qualified easy. We know how to do it. And technology is very good at doing that. Now, the opposite, which is systems that are designed to withstand high pressures, like Venus, for example, or in our case, our deep ocean, we're not very good at that. Or I'm not going to say that. We're great at that, but it just requires way more steps, more testing, more materials. It's as costly or more, again, as to sending a mission to space. So hence, if we were ever going to send some underwater vehicle or underwater system to other planets, we better learn how to do it on our own Earth, get better at that, and eventually be ready to do that safely in other places.
Right. Because in a way, you can launch this mission to the bottom of the ocean and pretend that you're on Europa.
Yeah.
And
Yeah.
you get the results in, and you ignore the shrimp for a little
Yeah.
while,
Yeah.
and you say, is any of this data coming in from the bottom of the sea with no preconceptions? Would any of this give us a signature that there is life in this vent, life in this ocean?
Exactly.
And you can use that as a test case.
Yeah, yeah, exactly. And one of the things we want to test, as with any space mission, again, a misconception is that when we launch a mission to Mars or to space, is that this is the most advanced analytical technology we can send. In other words, most people think that that this is the best lab ever built, and now it's flying to Mars because it's far, it's difficult, and it's NASA. And it's not the case. To be able to fly instruments, to fly experiments, to fly spacecraft, you have to compromise. And if you want it to work for a long time, if you want it to be safe, if you want it clean, so you don't contaminate other places, you need to sacrifice science. So you're gonna have to, very quick example. Most of the cameras we launch on Mars missions are less capable than your cell phone camera. And the reason is because it has to work. There's no room for failure. It has to be able to work in vacuum, on CO2 atmosphere, at minus 50 degrees Celsius. There's certain requirements that need to be met so that it works. So in this case, what we're trying to push is what kind of technology can we develop for space, for Europa and Enceladus, that can inform us to the best extent possible of whether there is life there or not. And that means that we have to be able to live without our beloved mass spec or our room-size laboratory instruments that are the best in the world. We cannot fly that. We have to fly something like the instruments we're testing so that we can learn whether, A, can we do the science we need to determine there is life there? Yes or no? If it's yes, then we develop these instruments to fly. If it's no, we build something else. And it's just the kind of process that not just our team, but NASA is encouraging other teams to develop missions like ours, go to an extreme place that looks like a place on space, and answer the question, can you do the job up there with the systems we have here? And that's kind of one of the main goals of our project, is to demonstrate that we can do life detection or understanding how life emerges or forms in our own planet, so that we can eventually do that in other planets.
Okay. And what about the timeline? So how are we looking for, when do you hope that InVADER will disappear below the waves?
So we launch, or we dive, I guess, in July 2020.
Okay.
So we have a very limited window. Think about Mars missions. You have a window. We have a similar window, and it's July 2020. So we're less than a year. Our countdown is less than 365 days, and everything's going to plan. Testing is going well, and everything seems to be aligning so that we'll be able to successfully launch our mission and say goodbye. Safe swims. In about 11 months.
Okay. And that's we were talking earlier, that's the same time frame as the Mars 2020 mission. So as they go up, you're going down, and that's very, very poetic.
What an exciting summer! And so not only the NASA Mars 2020 mission is launching in July next year, European Space Agency ExoMars mission, the rover mission, is going to launch about the same time, and the Chinese Mars 2020 mission is launching as well in about July-August timeframe next year. So within a matter of weeks, we'll be launching three Mars missions and one ocean mission.
Okay. We'll make sure that the publicity for yours keeps up with all these rockets going up.
Yeah, right. Yeah. It's going to be busy.
It's going to be very, very exciting. Well, that's fabulous. We've come up to the half-an-hour mark, and it's been wonderful talking. If anyone does have any more information, please do keep writing in to our Facebook page. Obviously, you can get in touch with Pablo and his team. If you have any other questions, take a look at their website. They've got some really cool descriptions and videos on exactly what InVADER is doing and how it's going to perform its science. So thank you very much. That's fabulous.
Oh, thank you.
Yep.
Bye, everybody.
Bye-bye.